Now we're going on to topic 5 of chapter 9, natural logarithms and changing bases. Well, one of the things I think is of interest at this stage is to look at something I saw actually on YouTube as I looked at other professors doing things. And one of the things they said is when we have a logarithm, let's say log of base 10 of 100, what is that? Well, that's going to be 2. And what is going on here in regard to logs? Well, if we think of log as some base that will equal raised to an exponent out here, some answer. So you remember that little way I said when you see something like this, think of it as there's your base. Now what goes here is we're going to raise this base to some exponent, and that will equal an answer. So 10 to the what power is 100? And the answer is 2 here, 2 to the second. So in logarithms, it's just another form of exponential notation. And natural logs are considered base 10. And you'll see that sometimes we don't write the 10 here. We'll say the log of 100, implying that it's base 10. All right, well, let's go on because we're going to introduce another logarithm base widely used today, and it's an irrational number that we will label the lowercase letter e. Now, do we know other irrational numbers? Well, remember we had pi was irrational, and the square root of 2 was irrational, and that simply means that when we convert it to a decimal form, it doesn't have a repeating pattern or doesn't terminate. That's from chapter 1 stuff. Okay, so let's take a look at the base e and natural logarithms. Now, one of the formulas, if you were in finance and finite math, is a course I taught years ago. We use this formula quite a bit. And this is when interest is compounded or computed n times per year. The compound interest formula is this. This will be your amount at the end. This will be your initial investment or principal. And then in parentheses, we have it 1 plus the rate divided by the number of times you're going to compound it. And it's that number of times per year, by the way, that you're going to times that by the time, which is, in fact, the number of years. So there's the formula. Now, if we were to have $1 as our initial principal, that would just be a 1 there. It would be basically this formula then, that we would raise to some period of time. Now, suppose this period of time is 1 year. Well, let's take a look at that here. It's on the next page. And they've developed a little chart for us here. And what happens to the function values of this when it's raised to that period of time it will be compounded? So as n gets larger, what happens? Well, when it's 1, when n is 1, this is 1 over 1, which is 2. 2 raised to the first power, because this is a 1 also, is just going to be 2. So again, you would never be able to get your money doubling after 1 year. That would be outrageous interest there, but that's if it were 100%. Anyway, you would have $2. Now, how about if you were going to compound that semi-annually, which means twice a year? So your n value then is 2. So you put a 2 there, and you're going to square this. Well, this then becomes 1.5. As you add these two together, you don't have to, you can convert this to a decimal fraction, 0.5, and then you're going to square that. Well, this becomes 2.25. Now, as you put a 4 there, this will become a 4. This is going to be 1.25, but you're going to raise it to the 4th power. If you put that in your calculator, you get 2.44. So what has happened? As you compound something more frequently, as n gets larger, these values get larger. But they don't get larger infinitely. They just get larger up to a certain point. Now, if we raise this up a little higher, and I tried these with my calculator, by the way, for this one, and I just plugged it into my calculator, it would be 1 plus 1 over this number, 8760, and that is, you are going to compound it hourly. Remember, there's 24 hours in a day, and if you times this by 24, you get this is the number of hours in a year. And then you have to raise it to this power. Well, this gives you a number, and if you tried it with your calculator, it would be 2.7181, and it would continue. So as you do this, what do you observe? Is it A, that as it gets large and very large? No. Does it get small as this gets very small? Does this get large? No. But as this gets larger, it approaches a certain number no matter how large this gets. And this number that it approaches is called E. This is what the variable E is. The number in the table approaches a very important number in mathematics. We call this number E. And because e is irrational, its decimal representation does not terminate or repeat. It is an irrational number. And approximating it to about 4 decimal places is this. As you can see right here, let me see, 28. Actually, we have to round this off to make it a 2. If we approximate that to 4, 1, 2, 3, 4, no, it's actually going to be a 3. Now, this is going to get much larger, and then you get the letter E. Okay? So rounding it to 4 places, we will have 2.718. Now in the 5th place, there's an 8. So we raise the 2 to a 3. And that would be an approximation to 4 places. And that means 4 decimal places. And what is that? Well, that's the letter E. Okay? Now we'll use this because this is also, since it's in a sense an exponent, a form of logarithm. Let's go on. So numbers, logarithmic bases e are also called natural logarithms. And the n in the natural often refers to John Napier or Naperian logarithms in honor of this fella who first discovered logarithms. The abbreviation IN, you might say, shouldn't it be N, I should say LN, shouldn't it be NL for natural logarithms? The thing is, in Latin, this is Logarithmus naturalis. It's written in reverse. So that's where the LN comes from. Thus, when you see something like this, LN, this is natural log 53, or the log natural, or the log base E of 53. And you'll have to practice this. This is sort of like another language for most of us that we have to practice to master it. Remember, take good notes so that you can use this as a reference as needed. Now, throughout this section, you're going to be pretty much required to use your calculator to figure these things out. Now over here they give us a student tip. Is your answer reasonable? And if you were going to say 5 squared and you got an answer 10,000, that's not reasonable. So you might say, well, I had it in my calculator and this is what I got. Well, again, if by accident you hit the wrong key, you're going to get the wrong answer. Now, there might be a possibility you would get something right, but more often you're going to, and 99.9% of the time, you're going to get something wrong. So you have to look at your answer and say, does it seem reasonable? That's why this is a study tip here. So I have a graphing calculator, and I also have like a regular standard Casio calculator, the ones we use in class. And they have both of these keys. They have a natural logarithm key, and they also have a log key. So again, depending what they're asking you to do, here you would, if they wanted you to find the natural log of 8, you would go on your calculator and hit natural log 8, and usually it comes up with a parenthesis, so you have to add another parenthesis, hit enter, and then when you round it off to 4 decimal places, this is what you get. Now in the graphing calculator, we have a really big screen. It looks like this, and a little screen, it would look tinier and much more narrow. It wouldn't be so, uh, this distance would be less. It would be right about there. Okay, so again, you're going to have to practice using your calculator to view the results of examples they give you. And of course, that would be allowed. So what I did is I followed these instructions, as I would strongly suggest you do, because the answers are there, and you have to practice using parentheses. And here you're going to put a +1. Notice that once you find this, +1 just adds 1 to this. And again, putting it in just like that, where you put E, and some of your calculators will have the letter E on there as well. But again, that's just the natural log and of this. And then the same thing here. Just here, this is going to be 2 divided by 3 in parentheses. And it gives you this. And for this one, it's just going to be E caret to put in your 2. Put that in parentheses. Then you do divided by 3. Again, it will take a little practice. All right, let's go on. Now, changing logarithmic bases. There is what we call the change of base formula. For any logarithm base A and B, and for any positive number m, this is the formula for changing bases. So again, I strongly advise that you write this down. And if you can memorize it, that would be great, but you can use your notes to do these examples. And I won't read it to you, but we'll see it worked out here right now. And by the way, they are giving you the proof of this. Let x equals log base b of m, and you have base b raised to x. Remember, x is the answer, and equals m. X is the exponent, equals m is your answer. All right, so let's study this here. So here they're just putting where m is, right there. They're putting what it equals. Equals log a m. Okay, that's good. Now remember, when you have an exponent, you can place that exponent in front, and you're going to multiply by that. And then you're going to solve for x, you're going to divide both sides by this, and that's what you have. And if you physically write this out, That's a good way to check your work and to see if step by step it makes sense. So what do we do? This is our change of base formula. Well, the key is we have to identify our M. We have to identify our A. And we have to identify our B. So here they're saying log base 5 of 8 using the change of base formula. Well, 5 will be our B right here. 10 is going to be our A right there. And M is going to be our 8. So we substitute then these values into our change of base formula. So we get log 10 of log 10 and then of 8 of 5. So what we put into our calculator is log, and if you're using the standard log of base 10, it'll just be log 8, you have to put another parenthesis, divided by log, and again the 10 is assumed, you don't have to put that in, divided by 5, put a closed parenthesis, and it actually would look like that. It doesn't show you that, but that's what it looks like. And then you just hit enter, and it gives you this. Now on my Casio, all I had to do is go log 8, no parentheses, divided by log 5, and I got this. So keep in mind that there is sort of a shortcut here. When you see this, when it says log base 5 of 8, all you have to do is divide 8, log 8 by log 5. Wow, shortcut. But again, be sure you write these out as an example, as models of what you'll need to do to get answers. So for this one, and now we're using natural logarithms, but it's just going to be, since they're giving you E here, it's just going to be log 31 divided by log 4. Now I did it with logs. You could also use natural logs, that would be the E value, and natural logs of this. And again, practice is what you do to earn or develop mastery. You want to develop your techniques for doing these. Okay, now again, some of you or most of you may not have graphing calculators. So again, taking notes on what it looks like will take care of it if you don't have a graphing calculator. So let's look at these as we move on. And again, taking notes. It says graph the function of natural log raised to the x power, or the function of its opposite, its inverse, that is that. And notice what happens when you do it. Here are some values for it, and there you get your typical curve of this, which is the function of natural logs raised to the x power. And then the inverse. And then let's compare these. As you compare them, can you see that one is the reflection of the other? This is its regular, this is its inverse, and it's reflected along the y-axis. So this y-axis then, remember, could be written as x equals 0. X equals 0 is the y-axis. And that's all I'm going to ask you. And you're going to just have to remember what it looks like when you have your practice and quiz me. And this is it. I'm not going to ask you to plot all these points, which you would need your calculator to do so too, but this is just basically a t-chart. Copy down anything you want. Now, what is the domain then of each of these functions? Now, an interesting thing, domain are our x values. So the domain of both of these, here it's coming from negative infinity and going over again eventually to positive infinity. That's for both of these. And for the range, here it's starting at, and notice it doesn't ever reach 0. That's for both of them. So it'll start at just above 0. That's why we have a parenthesis. And then it goes to positive infinity. Okay. Let's go on. Now here they want us to graph this. And again, if we had a graphing calculator, it would work out very well. Looks like that on a graphing calculator. If you did some points, it would look like this. Again, all I would ask you to do is to sketch some of this. And what can we observe? Well, here it's plus 2. So do you see that as this goes, that our baseline sort of is going to be y equals 2, but it doesn't quite reach the 2. So for our domain of this, it would be all real numbers. And for our range of this, it's going to start at 2, but 2 is not included, and go up to positive infinity. And this is a typical curve of this function here. And again, that is your natural log. Notice the use of the doubled up letter R here for all real numbers. Okay, so here, if we graph, now as we do example 5, we're going to graph and state the domain and range of each of these functions. So the g function of x is the natural log of x. And to graph by hand, we would find some solutions with a calculator and then draw the graph. As expected, the graph is a reflection of the line across y equals x, which we've used a lot in the past. Of the graph, y is equal to natural log to the x power. We can also graph this by using a graphing calculator. And its logarithmic function is the inverse of the exponential function. And we choose a viewing window that shows more. And again, we didn't do a lot with viewing windows. But here we're talking about values like so. So there is our axis of symmetry. y equals x. There is your exponential function, and there is your inverse function. And one is the reflection of the other. Now, notice in part B, we have something in which they're asking, and we include the 3 in our parenthesis. So when we graph it, and you may or may not recall that when something is in a parenthesis, not outside of it moves it up or down. This is going to translate 3 units over to the left. A plus 3 is a negative 3 units. Again, it never quite reaches the negative 3. And our graph looks like this. Again, I'm not sure how much of this I'm going to include on your test, but here is what they give. And again, if you had a graphing calculator, it would make this so much easier. Otherwise, again, you're just going to sketch this, and keep in mind that if you have a graph where they're asking you, this is the graph, and that's what you're going to match it up to. Now, here we're graphing log base 7 of x plus 2. So again, the plus 2 raises it up somewhat. And keep in mind the plus 2 is out all by itself. So when you graph this, again, it looks like this. And again, sketch it, put it in your notes. Okay, that wraps up our section 5. But I was looking at this part here, and I said, geez, this is very interesting here. Because again, a nice summary of all the things we've done. So what I think I'll do is I'll do this apart from our basic lesson, but we'll get back to this.